to the next section, the structure of our raster data. So we've already mentioned that each cell is usually quadratic, each cell, each pixel, and that each cell has to contain a value. Now this is not, generally speaking, a problem as such when it comes to continuous data, because that's what we want. We're after that. It's still going to be a large file, so to speak, but there is no better way of doing it. So that we can just keep in our minds and consider. But what happens then with our discrete data? Well, because discrete data is just describing things that exist, and there are no transitions between one thing and another. They are in one place or they're not. If we haven't described, if we don't in our ontology have that thing that is outside of the thing we're interested in, then what is it? Well, we get to this no data thing. And here we're exemplifying no data as 0, which is not actually always a very good number to use. In fact, in many cases, you shouldn't use no data equals 0, because 0 can be a thing as well. Usually we want some sort of extreme value that's very unlikely to occur, like minus 9,999, or if you're using floating point numbers, you can go to some extreme value way out one end that is not going to occur normally in your data. So it's easily identifiable as no data, whereas 0 can quite often be something. But so for our raster, I was going on about no data there, but for our raster, it means that because we have to have information for every single cell, where there aren't the things that we're interested in, we still need to say nothing here, nothing here, nothing here, nothing here, nothing here, nothing here. Oh, here's something. So it's repetitive, dull, but it's just what we have to live with when we're using rasters. So this is why it's inefficient. One of the reasons why it's inefficient for discrete data, because of having to store this repetition of not much happening, as well as the repetition of here's the same thing again, here's the same thing again. It's that repetition that makes it dull for discrete data. And also we have a problem with discrete data in that because we have these objects, or these classes of things that exist at particular cells, and they are discrete in their nature. We have a forest and we have a road. What about when we have road passing through forest? How do we describe that? Is there a continuum between there? Is it more road or more forest? Where do the numbers lie? What's the number line there between road and forest? That's very difficult. So perhaps we're tempted to create a new class, which is road going through forest. But what happens if we have several different types of road? A class of road going through forest. So you've already got, say you've got 3, 4, 5 different classes of road. So you're going to need all 4 or 5 classes of road plus 4 or 5 classes of road going through forest. But what happens if you have different types of forest? Oh, hang on, all of a sudden your number of classes you need to describe the data, they start blowing up. So again, we have this problem with raster data as not being a terribly efficient way of storing these class data, this sort of discrete data. But we can do it. So let's just look at storing discrete data in a raster. And we're doing this because we do it for particular reasons. There are some types of analyses that we are actually more convenient to do in raster, even though it's not a terribly efficient way of storing the data. We by necessity have to do this sometime. So what we've done here is, if this is our reality, it's a very simple reality. We have a couple of points, a line and a polygon. It's a strange blob here. Maybe these are houses or cities, and this is a road, and this is a lake, maybe. And we define those as, so whatever that thing is, this class of object, we'll give that the integer value of 1, and whatever this line is, this road here, well, that will give the integer value of 2. So wherever you see a 2, that means road, and wherever you see a 3, that means lake. And so in our raster here, we've got lots of zeros, our not particularly good no data. Actually, in this case, 0 can be no data because this is classes of information. So 0 is what we say it is. It can't accidentally be mistaken for something else, as long as we're careful. So here in class data, we can use 0. as no data. So that's not actually a huge error in this case. When it comes to continuous data, then 0 can be somewhat of a problem. There we really do need to be careful. But we've got this no data, so nothing happening here, nothing happening here, nothing happening here, nothing happening here, nothing happening. Oh, here's something. So here we have a piece of information. And when we look at this, we can see this road going down here, but the computer can't. We'll get to how it can later on, but let's just, to begin with, say it can't see anything. Each of these cells, each one is dumb. It doesn't know what its neighbour's doing. It doesn't care what its neighbour's doing. It sits there on its own, and I'm a 2, whatever 2 is. I'm a road. I'm a bit of road. Oh, and I'm a bit of road. Oh, and I'm a bit of road. Are they the same road? Well, we can see that probably they are, but that's not inherent in the data. There's nothing to say that this is one road. They just happen to be roady pixels that are next to each other. Roady, not like the big burly guys who move musical equipment around, but road pixels. And the same here with the 3s, the water pixels. If they're now water, that's what we're saying they are. So we've got all of this, and quite evidently these belong together, evidently to us, but for the raster, for the computer as it were, they're just pixels, and they happen to all have the same class. They don't belong together as such, not in no other sense than they belong to the same class. That doesn't necessarily mean that they are the same thing. They just have the same qualities, many of the same qualities. They're all watery, or whatever it is we're defining there. But this is in many cases fine. We have maps. This is a very simple map. This comes from a previous iteration of this course many moons ago, where we have a map of land use with water, woodland, and farmland. And all that's happened is that we have pixels where with certain numbers. So the green pixels here are woodland. So each pixel here has a value of 2, each of them, and each blue pixel has a value of 1, and each yellow pixel has a value of 3. And so we have all of this farmland and woodland and water. And we understand that they are these things because there's this table here, this attribute table that connects these numbers. These numbers are what's stored in the raster. This information is stored in an attribute table. And our understanding of what this means is stored in our heads. The colors, where they're stored, they may be stored in a file associated with this, but more often than not, they are stored by the project that you've created. In a GIS program that says wherever you see a value of 1, color it blue. Wherever you see a value of 2, color it green. Wherever you see a value of 3, color it yellowish, whatever that is. So that color is not inherent. It doesn't belong to the number in any way other than we say so via the computer. In the same way that 1 is only water because we say so in this attribute table. So these values are not there. They don't belong to these classes more than just because we say so. When we get to continuous data, this is continuous data. This is another form of continuous data. Previously we looked at an aerial photograph with colors, and now we're looking at a grayscale image, and this is an elevation model, a digital elevation model. But we can use it for other, we can use this type of raster for other things, precipitation or chemical concentrations, anything that we think would vary continuously across some form of surface. And we don't have this same connection to an attribute table. Rather, the values here stand for themselves. The description of what the values are supposed to represent, if it's elevation above sea level, pH, or something along those lines. But we just read off in each pixel, it is this particular value, whether it's several thousand meters or hundreds of meters above sea level, like this, or whatever else it is. But at the same time, as we can see here, our continuous data is actually stored in discrete packages in these cells of a homogeneous surface within there. But we don't say that that is a thing. This doesn't have any natural boundary, this square here or this square here. You wouldn't see on the ground any definite end to 1739.60-ish, whatever that quality is, which turns out it's a height above sea level here. you don't really, this generally speaking doesn't exist either as a homogeneous surface. The landscape doesn't exist as these squares either. This is just how we are representing the data. We need to step back to this level in order to be able to experience it, as it were, to see it more like as we would experience it on the ground, continually varying up and down smoothly. So that's what our continuous data looks like. Regarded from afar, it's continuous. When we zoom in too close, we get these discrete packages like this. And that is important to remember, that this is how the data is stored. It's continuous but discrete. And the same thing happens with, as we've seen, with our remote sensing images, with aerials, photographs, satellite images, that we have continually varying colors across the image so that we can see and interpret information in them. But that information, all the things that you can see in this image, and you've probably identified forests, trees, shadows here, farmland, some buildings, they don't exist as far as the computer's concerned. They're just colors. Our brains are interpreting those things into the image, but the computer, the data storage, does not see them as such. It just sees varying colors. We are doing a lot of interpretation of these things there. Now, if we move on to the resolution, the spatial resolution, we were talking about the size of the pixels. There's an interesting interplay between, specifically, we'll look at the spatial resolution. There's an entire lecture on resolution coming up later in the course, and this is not an easy subject. But if we simplify things down to spatial resolution, which is the hardest one to simplify down, but if we just say it is spatial resolution, we'll say ground sampling distance, how big is each square on the ground. When we look at continuous data with the elevation data or the aerial photograph, if we start down here, we have this red object, whatever that red object is, and then we have this grey background, something in the background there, and we can see that if we define our pixels, we have quite large pixels here, or large cells, however we want to describe this data, and we want to put a value on it. Well, it's mostly grey, but there is a bit of red in there. So because we have continuous data, we can define a value somewhere between the grey thing and the red thing, if they exist at either end of a spectrum. Maybe it's not actually grey, maybe it's white, and we're just using grey so things stand out from the background here. We have just this degree of redness creeping into that cell there, and we have a greater degree of redness creeping into that cell there, and likewise there, and even more redness creeping into that cell there. So we have this kind of fuzzy image. It's not very high resolution, but we can sort of see, we can imagine, okay, so the form of this thing is, it's got a greater bulk over here, less so here, and not much over there. If we increase our resolution, we can start to see that we get cells here that are quite full of this red stuff, so they're quite red, whereas these other cells, well, now in this top corner, before up here, when we were up around here, it was still a bit red, but now there's none of that red is left. It's completely absent up here, but it does creep in a little bit down there, so this becomes red, slightly reddish here, and likewise across these other cells. Still not a fantastic representation of this. So we increase the resolution again, and the same process is at work. Where we have a lot of redness, we get the deeper red cells, and where there's less, we have the grayer cells. And so we get this fading away here and this sharpening of this image over here. But of course, we're having to store more data. The value that can be stored in each cell did not change. It went from 0 to 255 in this case we're saying, but we needed to store more cells containing 0 to 255, one value there within that range for each cell. So it increased. We went from having only 4 cells to 64 cells. Now we can actually get a fairly decent outline of the image. But that was what happens with continuous data. So what happens if we do the same thing with discrete data? So now we're saying this is discrete data. There is no continuum. We can't say that something is more or less grey or red. It either is the thing or it isn't the thing. Either it exists at that point or it doesn't. It's discrete data. There's nothing in between. We have to make a decision. It is or it isn't. And this leads to a problem. Now, we were okay, if we've started this end now, we've got this reasonably high resolution image where we can form an impression of this object in much the same way. We don't have these fuzzy edges to it anymore. They're distinct boundaries. It is here, and it still exists in some form here. But for each of these cells, we've made a decision. We said, what's the majority of this cell? Is it red or is it grey? Mostly. And where it's mostly red, well, then we'll call it red. But if we say for this cell here, we can see that, well, it's not very much red, and it's actually dominated by the grey, so it's mostly the grey thing. So that becomes a grey. But still, we've got the object. In this case here, when we reduce our resolution so much, well, it disappears completely, because in no one of these cells is it the dominant colour. All of them are dominated by the grey background, so they become the grey thing, whatever that grey thing is. And so this disappears completely. Now, this is also the result of the position of the cells with regards to the object. So if this object had been further down to this one corner, or in any one other place, it could have dominated one single cell and would have suddenly been visible. But in this case, it happens to be at the junction between all of these four cells, and in no cell there does it dominate. And so it disappears from our data. So this is one of the issues that we have with discrete data in a raster as well. We can lose some objects depending on how we work with the data. In contrast to the continuous data, where you will always see some evidence, or in theory you should always be able to see some evidence of the objects that exist, as long as you're aware of the objects. They should exist at every location.